few words before we start. So let me explain today's protocol. I'll be the Genesis block, and then I'm going to introduce Ron, and then the previous speaker, like yesterday, will introduce the next speaker. And not only so, the previous speaker will also make sure the next speaker doesn't go over time, and he's bombarded with difficult questions from the audience. Okay, so if you are a speaker, remember you have to stay till the end of the next talk.
So can I extend my time and then use the time of the next speaker?
Okay, so the protocol needs to run robustly, just like Bitcoin, such that even if the co-chair, which is me, fell asleep in the middle of the protocol, when I came back alive and continue to participate in the protocol, everything should still continue as normal. Not that the speakers today will give boring talks, just that I didn't sleep well last night and didn't have enough coffee. Okay, so as today's Genesis block, I'm going to introduce Ron by telling my Genesis story with Ron, which Ron doesn't know. Okay, so this is how I met Ron. In 2004, I was an intern in IBM Research. I was interning in the trusted hardware group, not the crypto group. And then back then, like I was a first-year graduate student, I knew absolutely nothing about crypto. I didn't know that Ron was a big-name cryptographer, and that's why I was brave enough to send Ron an email and requested a meeting with him. And Ron was so kind that he blocked out half an hour to talk to me. And then he told me about what he was working on back then. It was this framework called universal composition. So I didn't understand what Ron was talking about, but I vividly remember that Ron was really, really passionate about universal composition. So that really, like, I remembered all these years, but what I didn't know back then was in a few years I would have tried to switch research area to crypto, and then in a few more years I would have found universal composition paper, like one of my favorite papers in crypto. And the paper is so fascinating in the following sense. Every time I read it, I think I understand it, but every next time I read it, I realized the previous time I read it, I didn't understand it. So just like the paper was written over like many, many years, you also need to read it over many, many years. So, okay, so I hope Ron's talk will...
Thank you. I just want to say that I'm the same. Every time I write it, I think I understand it, and then I realize that yeah, thank you. So this talk kind of came out with discussions with Len and Dalia. Actually, in the first workshop of this semester, there were lots of discussions about modeling and consensus and different things coming from different directions. And then we thought maybe it's actually good to actually give some talk about this framework, which can maybe help bring things together, because there are people here from many different areas, and in fact even more areas that deal with blockchains that somehow everything has to work together. And anyway, so that's a little bit like, when you have to be a bit grandiose when you talk about bitcoins, otherwise it doesn't work. So that's why the title. Anyway, so I can explain it better in a minute. So okay, so we want to do this public ledger, which is this amazing thing. It's not like the simplest thing ever, but it is amazing. That we just have this thing that keeps records for us. It's available everywhere. Everybody can access it. It doesn't cheat and it doesn't do stuff. But then it keeps records that come to it, and by anybody can put records there and keeps them in order, and maybe along also with some time of the registry. And there is some publicly verifiable, hopefully simple validity predicate that you put a record up only if it's valid, but maybe you don't even need it, but it's public and everything is recorded. So this is like the simplest thing ever, but it really is amazing, right? Because we don't have it, and if we had it, or we want to be building it, but once we have it, it doesn't, saying don't have it doesn't come in nature. And it really allows a lot of things to do, decentral currencies, global electronic commerce, a new world order with, people don't have to form into of countries and governments, and people can be think that in principle the world can be regulated in a decentralized way, and we can have the self-policing engagements, contracts, can even have things that doesn't have to do with economy, just a global records, a global record registry of everything that happened, history, public documents, all the deeds, the literature, art, science, everything is there as it happens, and there's no question of fake truth or not fake truth, what happened in which order, it's just there. But it wouldn't be amazing to have that in the world, Same way that we have, today TCP/IP, we just have a plug-in to this ledger and we see what happened when and what. So this is how kind of get introduced to this. So talking about Silvio yesterday about how he gives work. So this one, I think his first talk, he talked about Algorand a couple of years ago at MIT. He was giving this talk. It was a beautiful talk with lots of aqueducts and things about the history. And then he ended. That was the last slide of his talk. Oh, there was charging soldiers and stuff. But then I'm not sure it was this particular one, but it was maybe a nicer picture of Atlas, holding the world, and he says, "Thank you, Atlas. We'll take it from here." And that was the end of the talk, and that was, the way Silvio does it. And, we're thinking lately, is this like overly presumptuous in this? But no, it's not. And it's really, that's what this is about. And you can think of it, take it as a responsibility. It's, it's a good thing to excite people to get to work on it, but also a responsibility since we are doing something that should or can or has the ability to carry the world on it. Then we should be responsible to doing it right, to make it that it actually works. Sorry?
Premature hubris.
Yeah, but but actually no, it's not hubris. It's actually looking the other way. If this is what we're trying to do, we better take it seriously, right? In some sense, right? The other side. Yeah. Yeah, so the first impression that I thought when I saw this thing in the talk, it's hubris, but after second thought, not really. But anyway, so we're trying to construct this ledger, and we have all kinds of different things and primitives and animals going around. So the things that we like and know, and things that are new things. There's the PKI and the signatures and point-to-point authenticated communication, bound and delay, and then Eddie will jump. Why bound delay? Why not just synchronous? We'll make it cleaner. And then we have global clocks and local clocks and information dispersal and partial broadcast and all those puzzles and blockchains and leader election of all kinds. So we have all these things, and how do we make them work? So we can talk about different pieces, and different people talk about different pieces, but we actually want to make it work. And so it really has this feeling that we kind of like building a stack of cards, and how do we make it that it all works together? So like the cat in the hat. And you remember that is not all, right? My friend, this is not all. We actually want to build things on top of the ledger, right? So we want to build things on top of the global ledger. We're talking about decentralized currencies and this registry of events and this global library, and then privacy preserving things on top of that, because we want also to preserve privacy, and then smart contracts and distributed governance, and maybe we want to make it like work together with the law, because in the end we have to make things work with society and law, and so we want to have the whole thing work together, right? And it's not so easy, because one of those characteristics of this beast is that the reason that it works is actually pretty delicate, right? So there are lots of things going on there, and it's not that these are just applications that sit on top of lower primitives as we're used to. In fact, the fact that these applications there, they give incentives that actually give a reason for the security of the scheme to work, to exist to begin with. And so we have this kind of like seemingly intermingled set of concerns and guarantees and requirements, and which are not so linear as we like, right? Because much of the technology actually existed like 30 years ago, or 40 years ago, or 30 years ago, with this the company of Stuart Haber did these blockchains and everything, but it didn't work. It didn't fly. Why? In some sense, there were no incentives, right, for people to do it. And once the incentives came in, and things started to ramp up. So the whole thing is really kind of like one big circular mess in some sense, and unless you start to put order in it. But what we would like is to break it down, as we like to do as engineers, to break it down to simple models, and then analyze each model separately, independently of everything else, as much as you can, and then have simple proofs of security or whatever properties that you want from it, and then you want to be able to combine those models in a natural way and get this overall security, right? So in particular, you want to build those ledgers kind of in a systematic and layered way, as we know to do. And then maybe we can actually have one day some standardized notion of ledgers or components of ledgers, and we could maybe have this TCP/IP, this another layer to the network of communication, which is kind of a ledger layer that everything that is built in a layered way, and people just build on top of it without even thinking how it's realized, right? And this is really not what is happening today. What's happening today, you see, is those ledgers or currencies or whatever. They're built kind of in a vertical stacked way, in a self-contained way, and we have this separate stacks of things built, all the way from the beginning to the end, independently of each other, and which doesn't really work together. And somehow, in order to be able to work together, we need some common interfaces and security guarantees and abstractions. So this is kind of like the goal, and then how to do it. So it's not that I have concrete new solutions, but there's been work that has been going on. So let me try to give the basics. So what you want in this universally composable security. So what I'm going to do, I know for maybe some people in the audience, it's going to be a repeat or boring, but hopefully not too much. And I think I'm going to give the high level, because I think there are enough people in the audience that may have not seen a lot of it before, just to give the high level ideas of what's going on. Okay, so what is this universal composable security? So there are lots of, this is just a slide of credit. So lots of work in the crypto community about defining security, because it's important and it's delicate and it's hard, and different general frameworks and there are different composition theorems, and the UC theorem, the framework just evolved, as Elaine was saying, over the years together with that, and took from many of these, and it's not just a thing standing by itself. But never mind. Let me just describe now the basic of the framework. So here, kind of the CEO version of the framework. So we want to analyze security of protocols. So first we want the system to represent protocols. So in a very high level, so there is a protocol, which is this system of individual components. We call them machines. They interact in some way. Maybe I'll say a few words about it in a bit, but just think of it whatever way they interact. And the idea is to think about this protocol, the system, as the interfaces between the system and the external environment, which here is just it's just one single component. It's just a machine or unit or whatever. And there are two types of interfaces. One is like the input-output, which is a desired interfaces, what you want as an engineer. This is the input, this information of the system, and this is the outputs that you want. And this is kind of like the side effects, the things that you don't really need, and they don't help you, but they're there because the adversary, whatever, some people can see, because either it's the the leakage from communication or from corruption of parties or whatever. So this is a leakage of information here, and there's also some influence that goes from the system to your thing, the way the adversary influences your system via delays or whatever the adversary influences the system, and the idea, or maybe again behavior of corrupted parties, but anyway, so this is the two types of interfaces. And then you compare the system to kind of an ideal system. And this is kind of the specification, what you would want your system to look like. And the specification, as opposed to other ways of writing specification as a list of requirements, you actually write it as another system, which is your ideal system, which is naturally, you can think of it as one machine. You don't have to worry about distribution. Assume that they had one machine, and these are all the interfaces, again, all the APIs from the external environment, the inputs and the corresponding outputs. And here there are also side effects. And here you're writing, since you're writing specification, you're writing the side effects that you are willing to tolerate. So what information leakage you're willing to tolerate from the, to leak from the system to the adversary, to the external environment, and what is the tolerable, influences that you are willing to incur. And this is, this is a specification. So, okay, so and you want to say, again, the first attempt is to say that a system is secure or realizes the specification if no external environment can tell whether it is interacting with the system or with the ideal specification, right? So that's kind of like the notion that this kind of the observational equivalence of Milner, for the distributed people here, or the concurrency people. So this is like the basic the requirement, except that I kind of like partition the APIs for, with side effects and real ones. But this is too strong, right? Yeah. Yes.
In big pharma, they distinguish between the medicinal side effect. But the truth is that the difference between side effect and effect is very unclear.
Right.
So what is here the assumption how the side effect is different from the...
Great question. I'll pay you later. Answer in the next slide. Yeah. So the question was, what's the difference between side effect and whatever API, what I call the API? Is in this picture there is no difference yet, but the point is that this picture, the requirement is too strong. It's way too strict. We cannot many times we cannot realize it, because the thing is that often our system is actually different than ideal functionality, right? Ideal specification. So in particular, the specification is one machine. Here are the many machines. So of course, this would look different because environment can tell, because just because here the communication going on between machines there is no. So so you cannot do it. It's too tight. So what you want to actually relax it. And when you relax it, this is exactly where the difference between the side effects and the API comes in. Because now what I'm going to allow a more relaxed notion of to realizing an ideal system, and but I mean I'm going to add here a machine, kind of a fudging machine, which I'm going to call a simulator because of historical crypto reasons, and this machine. Now I want to say that the system P realizes in specification F, if there exists, that's part of the other list can do, or the protocol designer, if you want, /analyst, to come up with an S such that now this S sits between the environment and the specification on the side effect links and can translate things to each other, right? So now this is the requirement. So there is, there is a simulator such that for any environment, there is no way to distinguish, right? And then, okay, you would want, to put restrictions on S, but so now what is the meaning of this? So obviously this is weaker, but what is the meaning of this? So, okay, so this is what I said. So what is the rationale? So here's what's the rationale for adding S. So you can think of it as that any manipulation, that P, the protocol, can do to E, I mean, any leakage of information from P to any leakage of information from P to E could have done also in this ideal process, in the ideal specification by adding S, right? So any leakage, or maybe a better way to say it, any leakage of information that leaked from P to E could have leaked also in the ideal process by just adding S, right? So, so in particular, that would mean, if I go back to the picture, that here there was there was communication between the parties, and here there is no communication between the parties. That means that now the simulator will have to generate something that looks like communication between the parties to make E think it's here, and it has to do it based only on the information that it get from F. That means the communication between the parties doesn't leak more information than whatever is allowed. Okay, so that's the one thing. And the other rationale is just looking the other way around. Again, that any side effects that E can do to the protocol via those side effects links could have been done also to the ideal specification F by using S, right? So in the same way, S should be able to take any side effects to any manipulation that E wants to do to P. You should be able to do it also to F, again using the interface of allowed interface here.
When you talk side effect, you talk about the theoretical level, because a lot of people talk about side effects, and it's in the implementation. How much heat the machine gives.
You could model this. So this is a general framework. You can apply it, and that's kind of, in some sense, the beauty of it. You can apply it to anything. You can apply it to heat. You can apply it to delays. You can apply it to just information communication and the combination of the above. I mean, you can think of it at any level, right? So you want to say that the heat doesn't leak information on the secrets. That would mean that that your simulator will have to generate kind of heat signals that will look just like what the protocol does when the simulator knows nothing, say, about the secrets.
How do you consider the space of implementation is something that we don't know how to
So no, you're right, and what it means that we'll have to specify more what it tells the machine model. What I mean by those arrows, the actual model of execution all goes down to the details as usual. Yeah, this was taking 20 years, but yeah. And so yeah.
That's often the case, that the implementation has got all sorts of attributes that you don't even want to talk about in the spec. Right? And the implementation might have heat, it might have vibration, might have electromagnetic signals, which you surely don't want to talk about in the spec.
Right. So one way to do that is again, it's how you write the specification. So you write the specification saying, here are the things I care about. In terms of functionality, I want to give these correct things. And here are things I don't care about in terms of releasing information. There are things I'm going to give the interface. I'm going to let the simulator or whoever ask me information about things I don't worry about leaking. And things that I don't want to leak, I will not tell. So if the simulator asks me, features that I don't care about giving away, then I will give away. And also, if I don't care about specific aspects of the functionality, I don't care if if my output has 5 bits or 10 bits, but I don't want it to be less than 5 and no more than 10. Then you can allow the simulator to tell you how long the output should be, but you just put a limit here. So again, you model how much influence you allow up to your limits. So it all depends on again, the specification. The thing is that your specification should be written as a program for this to work. Which raises another issue, is how to understand specifications, because even when it's a program, maybe it doesn't mean what you think it means, but that's another issue. So anyway, so this is like the basic, and this is in some sense this is it. This is the whole thing, and now everything else is details of up to the model of exact pinning down what we mean by communication and information moves around, etc. Okay. So, and by the way, but this means now the definition is no longer symmetric, so if the protocol realizes functionality, it doesn't need the functionality to realize the protocol, which is, it's a good thing, right? You want to have many different protocols realize the same functionality. In the same way that one protocol can realize many different functionalities. But anyway, but we called that, our goal was modularity, and also the side goals of guaranteeing security in any environment. So the methodology of achieving both goals is this composition operation. So what we take, what we want is just this mechanical operation of composing together systems of protocol, so that can, on the one hand, express most natural composition operations that we think about in reality, and also preserve security. And here's the, again, in very pictorial terms, here's the composition operation. So what you have, as soon as you have some protocol, I call it rho. I draw it in one box, but you can think of it, this protocol can have, it's a distributed protocol. There are many components here that talk to each other. But I put them together under one box. They all say run the same code, and they know that they talk to each other. If by some way, say there's some session ID that combines them both, or maybe some other means that I can say these guys talk to each other. I want to call them a protocol. And this protocol, I said, has subroutine to another protocol, which I call phi. And what does it mean? See, if I have as many different instances of phi, I mean, they could have one instance or many different instances, but each one of those instances also is a distributed protocol, right? So I can think of so one session of TLS, secure communication protocol. If I think of it as one session that has secure communication that has many key exchange subroutines, right? If key exchange is one subroutine inside the secure communication. And each one of those, so maybe this is a multi-party thing, each one of those has two parties, etc. But never mind, this is the subroutine, and that means that if, locally with each party, it's just one protocol, one process that has sub-processes, and that process talks to other processes. So the subroutine is defined locally and also defined globally. And what I'm doing, I'm just saying I'm going to replace the subroutine of one protocol with just another protocol. Just replace just normal subroutine replacement, substitution with one subroutine with another subroutine, but it's done kind of like in a distributed way everywhere, in all the parts of the system. So that's the operation essentially, right? It's a very simple syntactic operation, but the idea that it really captures everything that we say, because let's see what the theorem says, and then you can say that it captures. So what the theorem says is that if I have two protocols that now I'm thinking the pi, such that pi realizes phi. Now I'm thinking of phi not as an ideal specification, but just another protocol, which makes sense. You can also talk about realizing another protocol, right? So if one protocol realizes another protocol, phi may or may not be an ideal specification, right? Then, for any protocol rho, when I replace pi with phi or phi with pi, I get a protocol that realizes the free elements. Let me say it more clearly. I start with a protocol that that is a row with subroutine calls to instances of phi. Think of it as specification of more ideal protocol. And now I replace it with calls to the actual implementation protocol pi. And what I get here is this whole protocol realizes this protocol. Okay? So if this is again a key exchange, secure communication protocol and uses ideal key exchange, whatever ideal key exchange means, and now I have a key exchange protocol which I analyze separately that the key exchange realizes the ideal key exchange, then if I plug in the real key exchange instead of ideal key exchange, I still get the same thing. Security-wise, but both correctness and security with this definition of before. And this allows for modular design, as you can imagine. Okay. Okay. And this can be done. It's another thing that So there is. You can think about cases that actually happen in life a lot. Fortunately or unfortunately, that we have systems where you have many different protocols that use the same. Or let me say the following before I do that. Here, this composition theorem is limited in a sense in the way that I can only kind of like do composition for primitives that don't have any joint state or joint information between them. So say here I have the two instances of ideal key exchange. I can only replace them with two instances of real key exchange if they're separate. They don't have any underlying common information. However, specifically key exchange, we know that the normal key exchange protocols, you don't just, you need some underlying basic authentication mechanism, say public key infrastructure, right? And then we don't live in this beautiful world because our two separate key exchange protocols actually use the same public key infrastructure. And then I cannot use this off the bat because it doesn't fit the framework. So you have to do something to make it work even when those protocols have some common infrastructure, common with everything else. So this is something that it exists if the protocol realizes the ideal specification with respect to some say global, non-global infrastructure or functionality, then you can still do this even with this global thing. And this is something that that was realized later. I'll tell more stories about it in the end of the talk. But anyway, so this is kind of refinement, and actually for ledgers it's important because we think of a ledger as one basic thing that we're going to use with many protocols, so it's important. And also within the ledger, there is the random oracle, there is timing, all kinds of things that you want to use. You think of them as common resources that apply to many different protocols, so we need that a lot. But anyway, it can be done. There are, of course, limitations on when this works, but still it works. In fact, the way I wrote it here, it's in general. Okay. Another variant that I want to talk about, say in a bit, just to say that it exists and how it relates. So you can also talk about this thing that why insist on having a single simulator? You can try to make the definition more refined in the sense that you can talk about cases where the system, the protocol has multiple parties and there's different components that are separate from each other, and you want maybe to have to say that you want your interface, this simulator, to be separate, different one for each component, not one global simulator, right? So this would only make sense if also the environment would be split, or that part of the environment would be split a bit. But the point is that you want the simulator to be split. And so you kind of think of it as a local simulator. So you don't have one simulator that has global view of everything and manages to simulate this way, but actually it's local simulators that only control information known to some party or some component of the network. And if you manage to show security with respect to this more fine-tuned, refined notion of simulation, then you get things, then you can use it to capture things like, several adversarial parties that do not go combine together to one adversary, but they work kind of adversarially to each other. They're competing with each other. And and just to say that this way you can actually allow you to capture things like game theoretic things like equilibrium and stuff. Yes.
Can you explain a little bit why there is now two sort of these blue purple boxes for the environment? Oh, sorry, the environment is now like these two purple boxes. So
Yeah.
one that talks to one of the S and the other one that talks to the other S.
Right. Okay. So for this, okay. So first, I think I missed kind of. There should be some line here. So those things, it's not complete. They would communicate, but you communicate in a restricted way.
So it's two environments, but they talk to each other.
Yeah. So we can think of it. Yeah, or two parts of the environment they talk to each other only in a limited way. I mean, you don't need that. I mean, you could make the definition for any environment, but then it would be very hard to realize, because if here the simulators cannot talk to each other. I mean, but I'm saying that the point is, the important point is not so much that these guys are separate, but the simulators are separate, and this will give you the extra refinement. Yes.
What exactly does two simulators give you over here? Because you could have had one simulator simulating both of them together.
But that would be a weaker requirement. So maybe you want, you think of it that you want to have, you think about it, a game or a competitive game between two parties. And you think of this game is complicated, and I want to say that it has the same properties as a simpler game. The same game theoretic properties, a simpler game. So you want to assure this notion of simulation to simplify things. But then if you only talk about one simulator that simulates the two things together, then you lose the fact that the game, it's a competitive game. In order to keep the meaningfulness, you have to do the simplification process separately for each party.
So is the important thing that the two simulators don't share?
Don't talk to each other, yeah. They do the simulation separately, yeah.
So are the two simulators could think of being associated with the simulators that are associated with each player? Or?
For instance, yeah, one for each player, yeah. So if you want to have one game, say two-party competitive or whatever, five-party competitive game, and you want to say this actually is the same as another game, which is simpler, assuming something, then this allows you to do such a thing, yeah.
You mentioned that there might be some conditions put on the simulator, because otherwise it seems like anything can. I don't quite understand why.
Yeah. So why? So the point is that you will need to be able to simulate. I'm just trying to think about maybe it should be a concrete example. Say. I don't know. So you are doing a game that involves some digital signatures, right? And you want to say that you don't want to think about the digital signature protocol. You want just to think of an ideal signature functionality, and you want to say let's just get rid of the crypto and think of a game as it works with an ideal signature thing. And you say, okay, now I replace my signature scheme with an ideal functionality. And this is something that you can do separately because you can simulate, you can do this replacement separately within each party. But I think of another example of another simplification that doesn't make sense. By somebody giving you, you want to compete. I mean, I want the coin to be 0, you want the coin to be 1, and we can simulate it. The global simulator that just chooses the coin to be random. Sure, it can choose it, but then you lose the property of the game that you compete with each other. So maybe you can take it more offline. But this is the idea. Sorry. Yeah. That's it. So I think I'm actually taking more time than I wanted, but. Anyway, so just to say that again, that was the idea, the high-level idea. But then, of course, the devil is in details, and you need to figure out a system, a system model that that on the one hand is simple enough that you can work with, and the other hand it is expressive, that it captures real stuff and you can capture real concerns, right? And this is a challenge. And there are lots of things to how to do with this challenge, right? And there are actually different frameworks that do it in different ways. And you want the layers of framework, you want some programming language and stuff, you want to have some sliding scale of a framework. How do you build those things? So the way, well, in fact, so what are the kind of like main sticking points about how to make these things concrete? So there's the issue of, are you talking about what are the models? The models are, are you modeling programs, algorithms? Are you modeling actually specific systems, implementation processes? And so we want, at least as computer scientists, to model algorithms and say algorithm has many instantiations. There's the runtime versus the code, and so we have to worry about this. And then you have to talk about how to define the actual models of computation. What are the individual units? And again, you want to do it in a way that you can use it to do many different things, from heat to overall systems. So how those units communicate and generate messages, how they are addressing each other, how do they know identities of each other, and how is the execution done? Is there parallelism? How is the parallelism addressed, etc. So and then how to define protocols. So there's a lot of subtleties and different ways to choose one way or another, and you want it to make sense. And again, you want to capture attacks and physical concurrency, physical time, stuff like that. And of course, bounded computation, bounded resource, computational assumptions, etc. So all the things need to be done. So currently the system, you look at the paper. So there are two frameworks actually. So there is a simple one, which is much more basic. Fixed number of entities, fixed connectivity, nothing dynamic, nothing changes over time. But you get the simplicity, you actually get the ideas. It's relatively simple, but it's a concrete framework that you can actually work with. But if you want to do something more general, then there's this other rest of the paper that actually talks about, it tries to model things in the most general way to capture all the concerns that we've been talking about. So this is what it is right now. I think by now it's pretty stable already. And the point is that, okay, so the issue of whether to do this global stuff with global subroutines, whether you need a separate framework for that or not. Historically there were separate versions of the framework to deal with that, but now we can actually do it all within the UC. You don't need to change anything, which is actually nice from a modeling point of view. But the point is, one thing to say is that to keep things simple, so the underlying execution model is actually sequential and deterministic and very simple. So all this, none of this concurrency, non-deterministic scheduling, etc., it doesn't work with crypto anyway, but you don't need it because you can express everything other way. So it's essentially, components get activated one by one, sequentially, and pass talking to each other, etc., whatever way. You can still model everything. And there's a lot of work in the formal modeling work about how to do parallelism and non-determinism and stuff. And just somehow we don't need it. And it also interferes with crypto, yeah.
Maybe you already addressed this, but I don't understand why the model can only handle one protocol repeated many times, like pi and repeated many.
No, it doesn't need to. It can be many protocols.
Pi1 realize phi1 and pi2 realize phi2, and you can have an environment with pi1 and pi2 and pi3. You can, but the reason I say just simply to think about pi1, but of course this pi can be, you can think of pi itself to be many different pi i's in some sense. Well, just for simplicity of notation of thinking, yeah, but you could, yeah. Yeah, so yeah, I know, yeah, okay, so yeah, okay. So lots of things, never mind. And the point is that, okay, so I'm not going to go, you of course can talk a lot more. Sorry? Sorry?
flight to catch. I have a flight to catch.
Oh, I see. Okay, good. Thank you. So yeah. So anyway, so just to say that that today with this going back to what we're doing here, what we're here for. So the thing is today with today's cryptocurrencies and blockchains and ledgers. In fact, we are doing something very different than what was done traditionally. So, you know, I miss lots of names and references with the people doing, trying to kind of model the world in a UC or modular way in this new world. And so now we don't no longer have point-to-point communication. We don't think about authentication as a basic primitive, and the notion of synchrony, and the traditional thing that we've been doing kind of don't apply anymore. So instead, there are different primitives that people define and just build things this way. So there's the gossip network that, again, no identification, no authenticated communication in the traditional sense, no PKI, because you can't. And so instead, there are other things that's called the gossip network, which is the basic primitive. And then you assume some bound and delay communication. You have a random oracle. You have digital signatures, which is without PKI. And on top of that, you can build, those two things that we've been talking about all the time. You actually two different ways to get ledgers. One is this longest chain protocol, aka Bitcoin style stuff, and how to get blockchains that work, and from these ledgers. And alternatively, you can do this stake-based leader election or proof of stake-based protocols. And again, you can have another way to get the same ledger, almost the same ledger with different small differences. And then you can combine it with this incentive-compatible mining to give rationale. And then you get decentralized currencies, and that you can get even decentralized cash, meaning Zcash with all the crypto, the heavyweight crypto of Zenoid snarks built into it to get the anonymity for cash. But all those things can be done modularly. So either things that are published or in the works that I know of are doing this. So this is it. And just to say, nothing that I didn't touch, but I think it is important to touch. And I think if there's anything that can do it, I think it's something like the UC, which is how to deal with smart contracts and how to program and model them, and how to talk things about higher level stuff like human intent and things that have to do with the law and society, like how to capture contingencies that you can't expect, like things that you have to do in normal contracts, right? And they talk about reasonability of a contract and what happens, if there is a flood and whatever. So how to capture those things, and then how to encode them and be compatible with the law, and somehow have an interface language between with what we do and the law. And this ideal functionality seems to be something that could be done. That you realize technically on one hand, and on the other hand, it's language that can be used to do the law. Anyway, so that's it.
Questions in the break? Let's switch.
Okay. So